I will go through a quick revision of Fourier series properties, or discrete time Fourier series properties. And then, as usual, we will solve some examples. I'll not mention all of the properties of Fourier series, but I will just go through the most important ones, in my opinion. In workshop 5. First, let's agree on this notation. If we have a periodic signal xt, and we know that, or let's say its Fourier coefficients are ak, we usually just write like this. Might also write Fourier series, just to say that we can represent this xt in terms of those coefficients, and we know how to represent a signal in terms of those Fourier series coefficients from this equation. It's just summation ak exponential j k omega naught t, and omega naught is the fundamental frequency of xt, and we call those, or we call this as the kth harmony of xt. Also, we know that ak can be obtained using this equation. 1 divided by the fundamental period of xt and integrating over 1 period of xt. xt exponential is j k and then t dt. So let's agree on this notation, and I'll use this notation for all of the properties. First, Fourier series is linear. Which means that if we have a signal x1t, which is represented by ak Fourier series coefficients, and x2t with dk coefficients, then alpha x1t plus beta x2t can be represented using alpha ak plus beta dk. So the Fourier series coefficients for the summation can be obtained from the Fourier series coefficients of each of those two segments. So we have linearity, superposition and homogeneity. So this transformation is linear, similar to what we did when we were trying to see if a system is linear or not. So here we can do it similarly. Let's say Fourier series is a system. And this is some system. When we put this signal as an input for this system, the system gives me a coefficient. And we can see that from here that this system is linear by applying this linear combination of signals at the input. We get a linear combination of the Fourier series coefficients of those two signals. So the system is linear, or the Fourier series is a linear transformation. What about the time shift? If we have xt with the corresponding coefficients ak, if we shift xt by t naught, Fourier series coefficients will be multiplied by some um, by this term jk omega naught t naught. Okay. Notice here we have negative and we have negative here in this term. Time reversal. This is just a reminder, but you should be able to remember those properties because they are so useful when dealing with Fourier series. Time reversal. If we have xt with the corresponding Fourier series coefficients, if we do a time reversal, we'll have also reversal of the index of the coefficients in the same way. Time scaling is interesting. Those are the basic transformation that we use to do on the independent variable, time shift, time reversal, and time scaling. And since we know how to do them in time domain, now you need to see what's the effect of those changes in time domain, how these changes will be reflected on the frequency domain. For time scaling, if let's say you have xt with the corresponding Fourier series coefficient, if we do a time scaling by alpha, what will be the coefficients of this new signal? To find that, let's first, we agree that all of these signals that we are dealing with xt are periodic. They should be periodic for the to be able to find the Fourier series representation. The signal should be periodic. So this is periodic, the fundamental period with a fundamental period t naught and fundamental frequency omega naught. When we do time scaling of a signal, its period will be divided by alpha. If alpha is less than 1, then the new period will be larger than the t naught, which we said we're doing time expansion. When alpha is less than 1, the period will be larger, and we say that we are expanding the time of the signal. And if alpha is larger than 1, then the new period of the time-scaled signal will be shorter than the original signal, and we say that we are compressing the time, or we're doing time compression. So when t naught is divided by alpha, then the fundamental frequency is multiplied by alpha because omega naught is 2 pi divided by t naught. And if we multiply, let's say the new omega is 2 pi divided by t, and this new t is alpha t naught, then, sorry, it's not alpha, it's t naught by divided by alpha because of the time scaling. It's t naught divided by alpha because of the time scaling. Then omega will be 2 pi divided by t naught and multiplied by alpha. And this is the original omega naught. So this is alpha omega naught. So the new frequency is multiplied by alpha. So this is the only change that will happen to this signal, that the time will be compressed or stretched. So nothing will happen on the magnitude of the signal, either in time or frequency, and the coefficient will remain alpha k, but the representation will be different. When we write xt, let's say, is a summation minus infinity to plus infinity, AK exponential JK omega naught T. Now X alpha T, if we want to represent the time scale version, we get the same coefficients, but GK, instead of omega naught, we will have alpha times omega naught. So the harmonics are different now. Alpha omega naught T. This is so this is the only difference. The harmonics will be different because the fundamental frequency of the signal has changed from omega naught to alpha omega naught, but coefficients will remain the same. Let's see, what other properties do we have? We have the symmetry properties of the signals. Um, Again, xt has those coefficients, ak. Now, if xt is odd, ak will be odd. And if xt is even, ak will be even. Okay. And there's more to this. If xt is real, then the real part of the coefficients and the magnitude of the coefficients are even. The imaginary part of the coefficients and the angle or the phase of the coefficients are odd. Now, if the signal is real and odd, then the real part of the coefficients will be zero, and only the imaginary part will be there. And if it's real and even, then the opposite will happen. The imaginary part will be zero. The only part will be just the real part of the AK. Or in other words, the coefficients will be purely real if xt is even. We'll see that we might see this in one example later. I will show the differentiation and conjugation, the differentiation and integration, because those are also very, very important. I mean, not show, I'll review because I'm sure you remember them from the main lecture. If we have a signal with the corresponding Fourier series coefficients, and then if we take the derivative of this signal, the corresponding Fourier series coefficient will be just multiplied by j, k, omega naught. So, and to generalize this, after every time we take the derivative, we multiply by this term again. So if we take the derivative of order n for the nth time derivative, this will have j, k, omega naught to the n, ak. Similarly, we can see or we can tell what will happen when we do that. When we take the integration of the signal, or we take the integral of the signal. Again, if we have xt with the corresponding Fourier series coefficients, and then if we take the derivative of the signal from minus infinity till t, so v2, the Fourier series coefficients for this new signal. Let's say this is a new signal called yt, which is just the integration of x t from minus infinity till, or x2 from minus infinity till t, and the result will be a function of t. Similar to the integration, but similar to the differentiation, but here we are doing the integral, and then we just divide by jk omega naught. Those are very important. Sometimes you'll find it hard to find the Fourier series of some signals, but if you take the derivative or the integral, you'll get a simpler function, and then you can do the Fourier series for that function, and then to get back to the original signal, either multiply by jk omega naught if you did the differentiation, or divide by jk omega naught to get the original signal after doing an integration. I think I'll stop the review here, and then I do some examples. There's two more important properties. Actually, I'll just mention them quickly. The multiplication. If we have xt with the corresponding Fourier series coefficients, yt with pk Fourier series coefficients. If we multiply those two signals, the Fourier series coefficients for, let's say this is z. The Fourier series coefficient for this new signal zt will be the convolution between the Fourier series coefficients of ak of xt and yt. So it will be L from minus infinity to plus infinity. AL B K minus L. Or we can write AK convolution with EK. This is a discrete convolution. This for the multiplication. And similarly, we have similar property, but for the periodic convolution and periodic convolution. And this is different from the convolution that we know, as this one is done over one period, and the result is periodic. In this case, let's say we have it's worth actually noting here that those two signals should have the same period, xt and yt, with the same period. And again, if we use xt and yt to show this property, xt ak, yt ek, both of them have the fundamental period t naught. Both periodic with t naught with the same fundamental period. If we take the periodic convolution between those two signals, which is they are continuous time, so the convolution is integration over one period, because we are calling it or because it's a periodic convolution, x tau yt minus tau d tau. And in fact, this convolution is also it's another signal with the same fundamental period. And the Fourier series coefficients for this new signal, which is the convolution between x tau and xt and yt, actually the periodic convolution, the Fourier series coefficients for this new signal is just the product or the multiplication between the Fourier series coefficients of the first and the second, and scaled by the period, the fundamental period t naught AK, EK. Those two are also very important. When you multiply in time domain, you'll get a convolution in the frequency domain. And when you do a convolution in the time domain, you get a multiplication in frequency domain. And one last relation, which is very, very important as well, which is the Parseval's theorem or relation. And this basically says that if you calculate the power in time domain or in frequency domain, you get the same thing. Or in other words, the power is conserved in power domain or in frequency domain is the same. If you calculate it here or there, you'll get the same power. And it's actually expected. So we should not lose or gain power just by representing the signal in a different way. And that's exactly what we're doing when we do the Fourier series representation of a signal, of a periodic signal. We're just looking at the signal from a different angle. So we should have the same amount of power in the signal, no matter how we look at it. So in the Parseval's relation, it says that if you calculate the power in time domain of the signal, is the same as if you calculate it in the frequency domain. And we call this term is just the power of the cave harmonic. And we add the power of all of the harmonics in the signal representation in the frequency domain, and we get the power of the signal. And this is also the power of the signal. Those two sides are equivalent. Again, sometimes you might be asked to find the power of a signal, and it's not always easy to find this integral after taking the absolute value squared and then you take the integral. It's not always easy to perform this integration. And it's easier to go to the frequency domain, find the Fourier series coefficients of xt, and do this simple summation or simpler summation. In fact, not always the case. Sometimes it's easier to do this integral, sometimes it's easier to do this summation, but you need to check the signal that you are dealing with and to decide. Sometimes this domain is easier, sometimes this one is easier.